Good day, students. In this clip, we're going to be going over an example on how to find the average rate of change, slope and equation of secant line, and also the equation of the tangent line to a point. Okay. Before I take a look at the example, let's consider some formulas real quick that's going to guide our problem solving process. So let AB be an interval um, on the function f of x. Okay? Then the average rate of change on AB is basically given by the formula delta f over delta x, which is the same thing as f of b minus f of a. This is known as your rise. If you think about your slope formula, rise over run, delta f is basically the rise, okay? And then delta x, this is going to be f of b minus f of a over b minus a. All right, over b minus a. So if you remember the slope formula, m equals y2 minus y1 over x2 minus x1, this is exactly what we're talking about here, okay? And then this can also be written as, if we let h equals b minus a, this can be written as f of a plus h minus f of a divided by h. Okay, in this case, where b minus a is equal to h. Okay, so all these basically mean the same thing, the average rate of change. And then the other formula that I'd like you to know about is the instantaneous. The instantaneous rate of change. Instantaneous rate of change. The instantaneous rate of change is a change at an instant. So in this case, we have to peg our x value to a point. So instantaneous rate of change at x equals a is basically given by df dx. Okay, df dx. This is going to be evaluated at x equals a, and this is equal to the limit as b approaches a, limit as b approaches a, of, we can write it as f of a minus f of b divided by a minus b. Okay, I can write it in the same order, but it doesn't make any difference. Okay, it's exactly the same thing. And this can also be written as the limit as h approaches 0 of f of a plus h minus f of a divided by h. All right, so it means the same thing. And this can also be written as the derivative of the function at a. So we can also write it as f prime of a. All this mean exactly the same thing, okay? All right, so let's go ahead and take a look at the example. All right, so for this problem that we're going to work on, let's call this problem number 1. It says for the function f of x equals x squared minus 2x and a point p, which is 1 and negative 1 on the function, we're going to find the average rate of change on the intervals 1, 3, on the intervals around x, 1, 3, 1, comma 2, 1, comma 1.5, and 1, comma 1.25. So if you examine these intervals, what you notice is that our x, the h in this case is getting smaller. The second value, the upper bound of our interval, is heading towards the first value. Basically, x is going towards 1. So it's, in this case, h is 2. Here, h is 1. H is 0.5. And here, h is 0.25. So the second term in each interval is getting closer and closer to the first point P, which is has 1 as the x coordinate. So that's just a point to keep in mind. Now, after finding the average rate of change, we'll find the slope and equation of the secant lines on the same table. The secant line PQ1, the secant lines through these points, and it will estimate the slope at the point P using the table, and then we'll find the instantaneous rate of change using this formula that I showed you earlier, a variation of the instantaneous rate of change. And lastly, we're going to sketch a graph of the situation and label the secant lines and also the resulting tangent line that we found using the slope, using the instantaneous rate of change formula. All right. So first thing we're going to do, let's make a generated table that we can use to populate all the average rate of change for these intervals. All right. All right, so what we're going to do, we're going to create a 5 by 5 table to organize our information. So let's go ahead and sketch our table. It's going to be a little bit big. So in the first column, we'll have our intervals. So let's go ahead and label that. We have our intervals, interval, and our interval is going to be AB. So interval A comma B. And then the next column is going to be our points. So the points will be from P. P will be our x1, y1, the first pair of coordinates, to our q sub n, our respective q's, which will be the x2, y2's. All right. And now next we'll have the next column will contain our computation of the average rate of change. So let's write that down. Average rate of change, and that's delta F over delta X. All right, and we're going to be using the formula F of B minus F of A divided by B minus A. That's the formula we're going to be using to compute our average rate of change at our respective P of Q sub n's. All right, and then the next column will contain our the slope of the secant line. The slope of the secant line. Slope of secant line, and then the last column will contain the equation of our secant line. Okay, last one will be the equation of our secant line. All right, so equation of secant line will go in our fifth column. All right. Okay, so we'll start to populate each row using the intervals that we were provided with in the problem. All right, so for the first interval, let's go ahead and draw a line there. I'm going to use 4 lines, 1, 2, 3, 4. So for the first interval, we have, we're looking at, let's do that again. We're looking at interval 1, 3. Okay, so let's go ahead and write that down. 1, 3. Okay, so what are the points? Let's rewrite the function here so that we can easily generate our output values. The original function f of x was x squared minus 2x. Okay, so the original p of x1, y1 is what you get when you plug in 1. The x coordinate of p is x. It's 1. Okay, because this right here is your the x coordinate of the p. Okay, and then this would be the x coordinate of q. So 1 is the x coordinate, and then y is what you get when you plug 1 into this function. And when we plug 1 into this function, you get 1 squared minus 2, which is negative 1. Or if you look at the original problem, we were told that point P was 1, negative 1. Okay? So going from there to x2, this is going to be our x2. This is, if you look at this, is x1 and x2. So x2 is 3. So what's y2? Y2 is basically what you get when you plug 3 into the function. So when you plug 3 into this function, you have 9 minus 6. All right, 9 minus 6. 9 minus 6 will yield 3. Okay, so our output value here is going to be 3. That's what you get when you plug in 3 into this function right here, okay? All right, now let's find the average rate of change for first interval. So delta f of del n over delta x at p q sub 1. Oh, this is supposed to be q sub 1. I forgot to put it. So that's q sub 1 right there. It's going to be f of 3 minus, let's write that down. It's going to be f of, because we know that b is 3 and a is 1. So it's going to be f of 3 minus f of 1 divided by b minus a. B is 3, a is 1, 3 minus 1. Okay? F of 3, we already know what f of 3 is what you get when you plug in 3 into the original function. F of 3 is 3 right here. So let's put that down. F of 3 equals 3 minus f of 1 is negative 1 minus 1 divided by 3 minus 1 is 2. All right, if we work that out, 3 minus minus 1 is 4. So we have 4 over 2, which is 2. So final answer is going to be 2. Okay, so the slope of our secant line, slope of PQ is simply going to be 2. All right, so now what's the equation of the secant line going to be? Now let's use the point P1, the original point P, that's going to be the same in all the problems as our x1, y1. Okay, so our equation is going to be y minus y1, which is negative 1, so it becomes a plus y minus y1 equals the slope, which is 2 times x minus x1, which is 1. All right, so there goes the equation of our secant line. The secant line I'm talking about is PQ1, okay? The line that goes through this point and this point. All right, let's take a look at our next interval, which is 1, comma 2. So we're going to do the same procedure, okay? Remember, this is the first x, and this is the second x, x2. All right, so P doesn't change. P stays fixed. Remember, the other points are getting closer and closer to P from the right. So from P to Q sub 2, Q sub 2 is, we know what x2 is. We know that x2 is 2. So what is y2? Y2 is what you get when you plug in x2 into the function. So when we're plugging 2 into this function, we're going to have 4 minus 4. So 4 minus 4 is 0. Okay? All right, so let's go ahead and find our average rate of change, or the slope of the secant line. So delta f over delta x of the secant line p q sub 2 is going to be f of b, which is 2, minus f of a, which is 1, and that this is divided by 2 minus 1. That's b minus a, okay? So we know that f of 2, what you get when plugging 2 into this function is 0. So 0 minus f of 1, which is negative 1, that's not going to change. So we can express this as plus 1 over 2 minus 1, 1, okay? So we're going to have 1 over 1, which equals 1. All right, so the slope m of p sub q2 is going to be 1. That's the slope of the second secant line, the ones that goes through P and Q2. So the equation of that secant line is going to be y. Remember, we're still using the same point. We can use this point; it will be the same answer, but let's stick with this point. Okay, so y plus y1, y minus y1 is going to be y plus 1, because minus times minus is plus, equals m, which is 1, times x minus 1. Okay. Notice how the slope is changing. It was 2 before, now it's getting to 1. The ultimate goal is, what value is that slope, the slope of the secant line, what value is it approaching? That's the ultimate goal of this activity, okay? All right, now let's get closer to, let's get closer to 1. What we're going to pick now is 1.5. All right, so the interval that we're looking at now is 1 comma 1.5. So this is our new x2. So this is x1 and this is x2. All right, now let's find the 2 points that we're looking at. The 2 points that is determine the secant line goes through. Point P1, point P doesn't change. That's still going to be 1, negative 1. The second point, Q3, is going to be x2, which is 1.5. And then what's the output here? What do we get when plugging 1.5 into this function? Well, it's not that easy to do the computation. If we use 3/2, it will be easy, but it has a lot of arithmetic. So let's make use of our calculators here. All right. So let's see. There are different ways you can compute output values of a function in a calculator. You can use a table, you can define a function, or you can use a graph. So let's go ahead and use the graph approach here. So Diamond F1 takes you to the graph menu. We're going to enter the function that we're working with, x raised to the second power minus 2x. Enter. Now, we're going to plot our graph. So Diamond F3 will generate our graph for us. So there goes the graph. All right. So what I really care about is the output values. So I want to figure out what the y coordinate is when x is 1.5. So to do that, what I'm going to do is I'm going to use the trace option. So you press F3. F3 allows you to determine the output given any specified input value. So now let me do the other one. So for example, for the first set, if I enter 3, what do you expect the output to be? To be 3. We calculated it earlier, that's good. For the second one, if I input 2, let's put 2, what do I expect the output to be? Should be 0, right? Enter, we get 0. We already knew those. The one we need is 1.5. So we enter 1.5. Okay, let's fix that. 1.5. Press enter. Negative 0.75 or negative 3/4. Okay, so our output value, or y2, is going to be negative 0.75. Okay, now let's compute the average rate of change, or the slope of the secant line through these 2 points. That's going to be delta f over delta x at evaluated of the secant line PQ3. Okay, so that's going to be f of b, which is 1.5, minus f of a, which is 1, divided by b minus a, which is 1.5 minus 1. Okay, so if we do the calculations, we're going to have f of 1.5. We already know that it's going to be negative 0.75. So negative 0.75 minus f of 1 is 1. So minus 1 is negative 1. Sorry, so minus negative 1 to make it plus 1, divided by 1.5 minus 1 is 0.5. Okay, we can compute this in our calculators real quick. Let's go ahead and do that. So let's say we have, let's go home, parentheses, negative 0.75, negative 0.75 plus 1, divided by 0.5. And your final answer is 0.5 or 1/2. Okay, so it's going to be 0.5. Let's use a decimal representation for that. So it's 1/2. 0.5 is the same thing as 1/2. So it is equal to 1/2. All right. So the slope here of the third secant line is equal to 1/2. So what's the equation of our secant line going to be? Y minus y1 minus minus 1, since y1 is negative 1, is going to become y plus 1, equals the slope, which is 1/2, times x minus 1. All right. Okay, 3 down, 1 more to go. Notice we're getting close to 1, right? So as the x2s are getting closer and closer to x1, notice what's happening with the slope. It's dropping. We have 2, 1, 1/2. Let's get a little bit closer to x1 and see what happens, all right? So let's look at the last interval that was indicated in the problem, which is from 1 to 1.25, okay? This 4 points is sufficient for us to speculate as to what the slope of the tangent line or the instantaneous rate of change is, okay? So P is always the same, 1, -1, to another point on the line, Q4, which is our new secant line. And our new secant line has a b value, okay, this is x1, this is x2. It has a b value of 1.25. Okay, so what's the y coordinate of Q4? Or basically, what is f of b or f of y2? Well, that's what you get when you plug in 1.25 into this original function. We can do it by hand, but let's go ahead and use our calculator to figure it out. So let's go back to the graph we generated, diamond F3, and we're going to use the trace option again, and what we're going to enter is 1.25. Enter, and we have negative 0.9375. Negative 0.9375. Let's go ahead and enter that. Negative 0.9375. Okay, so there goes our point. Now let's find the slope of the secant line. The slope of the secant line through these 2 points. So delta F over delta X of the fourth secant line, PQ sub 4, is equal to f of b. B is 1.25, so f of 1.25 minus f of a, which is 1, f of 1, divided by b minus a, which is 1.25 minus 1, so 1.25 minus 1, okay? So the question is, what is f of 1.25? What is it? Well, that's what you get when you plug in 1.25 into the original function. So let's use our calculator to help us there. Oh, we already did it, so we don't even need to do it anymore. So f of 1.25 is this value right here. So it's going to be negative 0.9375 minus f of 1, we already know is negative 1. So minus 1 is going to make this plus 1, divided by 0.25. Okay? And then we can do this in our calculators. Let's see what we get. So if we do this in our calculators, let's go back home. So what we're going to do is compute negative 0.9375 plus 1 divided by 0.25. And our answer is 0.25, and we know that 0.25 is the same thing as 1/2, right? So we're gonna, 1/4, 1/4. So let's go ahead and write that down. So 0.25 is 1/4. That's our slope. So the slope of our secant line, m of the fourth secant line, p of q sub 4, is 1/4. Okay? So now we can write down the equation of our fourth secant line, which is going to be y minus y1 is still going to be y minus minus 1, which is y plus 1, equals 1/4 x minus 1. Okay? So there you have it. Now we can go ahead and close the table and shift our attention to the last portion of the next section of the problem, which involves estimating what the instantaneous rate of change is. Okay? All right. So part C, let's estimate what the instantaneous rate of change is. So what can we discern here? So option C, on part C, we're making a guess right here. The instantaneous rate of change at x equals 1 is, what do you think it is? You notice how it's getting smaller and smaller? It's approaching 0. So we can, let's guess, it looks like 0 should be um, a good guess. Okay? Approximately 0. But we're not 100% sure. It's approximately 0. All right? So sometimes you can make an approximation and it could be correct. Other times it might not be. It might be close. Okay? All right. So let's go ahead and determine what the instantaneous rate of change is using the formula. All right. So approximation. Now let's determine the actual instantaneous rate of change. So to do that, we're going to look for we're going to use the formula f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x, this divided by h. Okay? All right, so there are two ways we can go about evaluating this. We can plug in x equals 1 into this function and evaluate the limit, or we can evaluate this limit using the function first and then plug in 1 at the end. So let's find a general function to represent the instantaneous rate of change, okay? So we know that f of x is equal to x squared minus 2x. All right, so let's go ahead and evaluate what this limit is. So this limit is going to become the limit as h approaches 0 of f of x plus, since f of x is x squared plus 2x, that follows that f of x plus h is going to be x plus h squared, right, minus 2 times x plus h. Because f of x plus h involves replacing the x's with x plus h. Okay? So if we plug that in here, f of x plus h is going to be x plus h squared minus 2 times x plus h minus f of x. F of x is a function x squared minus 2x. And that whole business divided by h. Okay, this is going to tell us what the instantaneous rate of change is, and we're going to see how accurate our guess is. All right, so let's go ahead and simplify this. If we work this out, we have limit as h approaches 0. X squared, x plus h squared is x squared plus 2xh plus h squared. If we distribute negative 2 to these two terms, we're going to have minus 2x minus 2h. And then distribute further here, we'll have minus x squared plus 2x. And then this entire expression divided by h. Okay? All right, let's see if we can simplify this limit expression here. So what you notice is that this x squared and this x squared add up to 0. And then this 2x and this 2x add up to 0. So we're left with the limit as h approaches 0 of 2xh plus h squared minus 2h over h. Okay? Notice we get h is common in the numerator, so why don't we go ahead and factor that out? So we have limit as h approaches 0 of h times 2x plus h minus 2, this whole story over h. Okay? Now these two h's divide out, so we're going to be left with the limit as h approaches 0 of 2x plus h minus 2. Okay? Now to finish this off, we just use substitution here, plug in 0 for h, so we have 2x plus 0 minus 2. So f prime of x is going to become 2x minus 2. So what on earth is this? Well, this is a function that tells us the instantaneous rate of change of the original function at any x value. All right? So what about, we're asked to find the instantaneous rate of change at x equals 1. So f prime of 1, we're going to set x to 1 is going to become 2 times 1 minus 2, which is equal to 0. So we can see that our guess was actually correct. F prime of x is equal to our estimation. Okay? Now that we have that, let's go ahead and make a sketch of the situation and then label it completely. All right, so let's graph some points. Let's set up our coordinate system first. We have our y coordinate and then our x coordinate. If we look at the graph from the calculator, we can use that to guide our the construction of our graph. Remember what the graph looks like. Goes through 0, 0, 2, 0, and 1, -1. And then at 3 is also 3. So let's use 4 tick marks to be 1 since it goes as far as 0.25. So 1, 2, 3, 4. Let's call that 1. And then 1, 2, 3, 4, 3, 4, 2. And then 1, 2, 3, 4, 3. Okay, and then on the y-axis, we can just go by 2. So let's call that 1, 2, 3. Okay, this is just a sketch. Let's graph the points. So we have, we know we have 1 point here, 0, 0, and at 1, -1, we have another point here, and then we have another point here, and then the last point was at 3, 3, which is right here. Okay, so the portion we actually care about is this side right here. Let's just sketch the graph. So the parabola looks something like this, like that. Okay, so this is just a sketch, all right? So let's go ahead and draw our secant lines. We have 4 of them. So the first one goes through from 1 to 3. So let's sketch that. So from 1 through 3. All right, so there you have it. Let's label what that one is. So this one is PQ sub PQ sub 1. All right, and the equation was y plus 1 equals 7 over 2 times x minus 1. This is the first secant line, okay? And then the second secant line goes through, it's from 1 to 2. So let's make that brown. I don't think that's good. Let's make that red. All right, so it goes from 1 through 2. There goes the second secant line right there. It goes through the same 0.11. So there goes the second secant line. And then this one is P of Q2. And the equation of that secant line was y plus 1 equals 1 times x minus 1. All right? Okay, we have 2 more secant lines to draw. The other one was from 1 to 1.5. We know 1.5 is somewhere at the center here, so it's going to be somewhere here. All right, so let's go ahead and draw that line. Let's make it green. Since it's getting a little bit, let's make it slimmer. All right, so let's draw that. The third secant line goes from this point through that point right there. Let's do it again. A line. All right. All right, so let's go ahead and draw it from this point through that point right there. All right, so what you see, you know, what is happening here is that the secant line is actually approaching the tangent line, okay? Let's go ahead and write down what that equation of that line is. So this is P of Q3, and the equation of this line is y plus 1 equals 1/2 x minus 1. All right? Okay, now the last one it'll be very hard to see. It's really, really close. So it's going to be 1.25, which is somewhere here. It's a point somewhere around here. Let's use blue for that one. So we have a point here, we have the point here, and then we had another point here. Kind of missed it a little bit. Let me fix that. That's deep enough. So that's Q3. All right. All right. So let's draw our secant line for this case. This one we're gonna have a. Let's make it blue. All right. It's gonna look very much like. It's gonna be somewhat steep, but not exactly horizontal. So there goes the the um, the fourth secant line. Okay, there goes the fourth secant line. And then let's go ahead and write down the equation of the fourth secant line. P of q sub 4 is y plus 1 equals 1 over 4 times x minus 1. Okay? So what is our tangent line going to look like? Well, we know what tangent lines look like, right? Tangent lines are lines that touch the curve at exactly one point. But we know that the slope of our tangent line or instantaneous rate of change at this point is 0. So we know that it's going to be a horizontal line. So this horizontal line right here, shift it down a little bit, through that point, that line is our tangent line, and it has a slope of 0. Okay? So this line right here is a special line, is known as our tangent line. Tangent line. And the equation is going to be y, same as the other, y sub y1, y plus 1 equals 0 times x minus 1. All right? If we solve this equation for y, we're going to end up with y equals 0. So there you have it. Thanks so much for taking the time to watch this presentation. Feel free to subscribe to my channel by clicking down here or this link. And also, you can comment to let me know what you think about this clip, like or share with your friends via your respective social networking programs. More clips can be found on microsoft.com/calculus. Thanks again for watching and have a wonderful day.